and in this video I will be covering proof by induction. Say we have some predicate p of n, and we're trying to prove that p of n is true for all natural numbers n. We can do this using induction, which is a two-step proof technique. The first step in this process is the base case. Because we're trying to show that p of n is true for all natural numbers, we must show that it is true for the first natural number, which is 0. So in other words, we're going to prove that p of 0 is true. The second step is the inductive step. In this step, we're going to assume that p of k is true for some arbitrary natural number k, and show that this implies that p of k plus 1 is true as well. So in other words, in this step, we're showing that if p of k is true for some natural number, it is true for the next natural number as well. Now you might be wondering how these two steps in combination help us prove that p of n is true for all natural numbers. Well, if we consider the first few natural numbers, 0, 1, and 2, then notice that in the base case, we've proved that p of 0 is true, and in the inductive step, we've showed that if p of k is true, then p of k plus 1 must be true as well. So if p of 0 is true, then p of 1 must be true, and if p of 1 is true, then p of 2 must be true, and we can repeat this process forever, and thus show that p of n is true for all natural numbers n. Now let's put this technique to use with an example. We're going to try to prove that for all natural numbers n, p of n, which is the sum of the natural numbers from 0 to n, is equal to n times n plus 1 over 2. The first step in doing so is the base case, in which we are trying to prove that p of 0 is true. The predicate tells us that p of 0, which is the sum of the natural numbers from 0 to 0, which is just 0, is equal to 0 times 1 over 2, which is true because 0 times 1 over 2 is 0, and thus we have proven that p of 0 is true. Now we can move on to the inductive step, in which we prove that p of k implies p of k plus 1. So we're going to assume p of k, which means the sum of the natural numbers from 0 to k, is equal to k times k plus 1 over 2. This assumption is called the inductive hypothesis. Based on this assumption, we are trying to prove p of k plus 1, which is that the sum of the natural numbers from 0 to k plus 1 is k plus 1 times k plus 2 over 2. In order to show that this equation is true, we're going to start with the left-hand side and try to show that this is equal to k plus 1 times k plus 2 over 2. In general, with this part of the inductive proof, we want to start with one side of the equation and work towards the other. Recall that we assumed that the sum of the natural numbers from 0 to k is equal to k times k plus 1 over 2. So we can substitute k times k plus 1 over 2 into this part of our equation. If we do so, we get k times k plus 1 over 2 plus the additional k plus 1 term. Now the rest is algebra. We can multiply the numerator and denominator of this k plus 1 term by 2, and we get k times k plus 1 over 2 plus 2 times k plus 1 over 2. Now if we combine these two fractions, we get k plus 1 times k plus 2 over 2. And thus we have proven that the sum of the natural numbers from 0 to k plus 1 is equal to k plus 1 times k plus 2 over 2, which is exactly what we were trying to show in our inductive step. And now to recap, we have shown that p of 0 is true, and that if p is true for any natural number k, it is true for the next natural number as well. So since p of 0 is true, p of 1 is true. Since p of 1 is true, p of 2 is true, and so on and so forth. Thus, we can conclude that by induction, p of n is true for all natural numbers n. In the second example, we are trying to prove that for all integers greater than or equal to 4, 2n plus 3 is less than or equal to 2 to the power n. Since we are trying to prove that p of n holds for all integers greater than or equal to 4, our base case is proving that p of 4 is true. 2 times 4 plus 3 is equal to 11, which is less than 2 to the power 4, which is equal to 16. And thus, we have proved that p of 4 is true. Now we can move on to our inductive step, which involves proving that p of k implies p of k plus 1. We're going to start by assuming p of k, which says that 2k plus 3 is less than or equal to 2 to the power k. And we're going to use this assumption to prove p of k plus 1, which says that 2 times k plus 1 plus 3 is less than or equal to 2 to the k plus 1. In order to show that this equation is true, we're going to start with the left-hand side, which is 2 times k plus 1 plus 3, which is 2 times k plus 2 plus 3, which is the same as 2k plus 3 plus 2. Recall from our inductive hypothesis that 2k plus 3 is less than 2 to the k, so it follows that 2k plus 3 plus 2 is less than or equal to 2k plus 2. To reiterate, we know that this term is less than this term from our inductive hypothesis, So the left-hand side must be less than or equal to the right-hand side. Now we're going to use a clever trick here. Because we're only dealing with k's that are greater than or equal to 4, we know that 2 will always be less than 2 to the k. And thus it follows that 2 to the k plus 2 is less than 2 to the k plus 2 to the k. 2 to the k plus 2 to the k is simply 2 to the k plus 1, and this is exactly what we are looking to prove, that 2 times k plus 1 plus 3 is less than or equal to 2 to the power k plus 1. Now, since we have proved the base case and our inductive step, we can conclude that by induction, P of n is true for all n greater than or equal to 4.